All right, everybody. So, like I said, I wanted to come back and work through some of the data for you so that whenever I provide you with your data set, you know kind of what you're doing. Um, but I also wanted to go ahead and talk about like what our purpose is, what our intention is to do with this data. So, our goal is a little bit, I don't want to undersell it and say it's easy. It's not necessarily easy, but we have a pretty good idea of what we're wanting to do. And that idea is we want to take this data and basically linearize it. And then we want to look at what is the graphical representation that's going to give us that linear graph, or what is the equation that's going to give us that linear graph. So one of the things that makes working with our data a little bit challenging right off the bat, and I'm going to go ahead and share my screen so you're looking at the same thing that I am. This data right here, we have a total of 3 different trials, just like we did in lab yesterday. And these trials correspond to, let me see, where's my cursor? There we are. 0.5 milliliters of a bleach solution, 1 milliliter of a bleach solution, and 1.5 milliliters of a bleach solution. Now, this is a little bit different from what we saw yesterday because if you remember, our absorbance was about 632 nanometers, but we're going to go ahead and use this 633.5. It doesn't really change our results. But one of the things that's worth noting about this is all this. Let's go ahead and start right here. Cell number B5. I'm going to zoom in a little bit. Hopefully you guys can see it a little bit better. Nope, I'm on my that. So I'm going to clear my drawings. Clear my drawings. It's interesting. I had the option to clear all drawings or clear my drawings. I don't know who else has been drawing here, but at any rate, I've cleared all that. Okay, so we're starting with a time point of 0 for all 3 of our data points. Now, one thing that is worth recognizing about this is keep in mind what this number is. So this number, so in this first cell, B5, 0.19996373, and then in B6, 0.81819934, those are absorbances. Now, an absorbance is not a concentration. You know, if you look at these, if you think about what we were doing, we were detecting our FD&C, and we saw our FD&C concentration go down, or we saw our FD&C absorbance go down, indicating that we had a decrease in concentration. But it's important to appreciate and acknowledge that an absorbance is not a concentration. They are independent, or they are different. Now, you can correlate an absorbance to a concentration by using the Lambert-Beer law, aka Beer's law. And Beer's law is A for absorbance is equal to epsilon BC. Okay. Now, if we want to get concentration, what we can do is we can manipulate. Sorry, let me switch colors on my little what you call it here, my pen. What we want to do is we want to capture what that value is. So we can do the algebra to rearrange this equation. And once we rearrange the equation, I'll talk about what each value is. A is equal to, and then we're going to divide each side by epsilon B. And if you remember that B is 1 centimeter, and epsilon is our molar absorptivity constant. Okay, and the value that we got was something like 97,740. The true value for FD&C is something like 131,000, but we're going to use this 97,740. So what we're going to do is we're going to divide epsilon beta, or epsilon B, isolating concentration. So essentially what that means is we can take our absorbance, say this one right here, and we can divide it by, well, simply that 97,740. So in this piece of software, Microsoft Excel, it's kind of easy to do that. And I'm going to go ahead and, let's see, I can erase some of my markings, but not all of them. So I'm going to do that. Erase these, erase these, erase these. Okay, erase these, erase these. I know that I'm erasing a lot of it. Now I kind of feel like I should just erase all of it. But I'm going to leave that A equals EB. So what we can do with this is take equal sign, select this cell, divided by 97,740 times 1. Well, that happens to be 97,740. And that's what we get. Now we double click in the lower right hand corner and booyah, there's all of our concentrations. We can do that for each one of these absorbances. Divided by 97,740 equals this divided by 97,740. Oh, that's wrong. Typed in 97,740. Okay, corrected. Lower right hand corner, populate, populate. And that gives us kind of our first setup for the data that we need. Because what we need is we need data that shows us a graph that is, oh, that's absorbance versus time. We've got those values. We've got time over here, time over here, time over here. Or I'm sorry, not absorbance versus time. Oh, that's not in my eraser function. Eraser. We want to look at concentration. So FD and C versus time. And so now we've got our FD and C concentration here, here, and here. Okay, so we have all the data that we need in order to produce this plot. All right. So my purpose in finding or in doing this first graph, I went ahead and erased everything, is ultimately determine the order of my reaction. So what I'm going to do is highlight all my time points, and then hitting Control, I'm going to select this other data set here. There we go. I'm going to go to Insert and Scatter Plot. And what I've got here is a graph that shows me my oh, I don't know what that is. Okay, sorry, I don't know if you guys saw that or not, but I've got my concentration of FD&C versus time. My last time point was approximately 44 seconds, and my lowest concentration was 2.57 times 10 to the negative 6. My first time point was 0 seconds. Now, what I think is appropriate to do in this instance is, if you look at that initial time point, that 0 time point, and you look at the concentration of that, 0.00002, you can go ahead and delete that. And the reason for that is because of the fact that you were loading your cuvette, or we were loading our cuvette into the sample. Now, what we want to be able to do with this is we want to determine whether or not this line is, or if this data is linear. And just looking at this, I can kind of tell that there's a little bit of a curve, but a little bit more accurate than I'm feeling like there's a curve. We can go to Add Trend Line and then put in our R-squared value, because our R-squared value is going to show us basically how linear our data is. Our R-squared value of 0.9746 is an early indicator that we probably do not have a linear relationship. So now that we've come up with this graph and with a R-squared value of 0.9746, what we want to do is we want to be able to compare that. And what we're going to compare it to is our other graph, where we're looking at the natural log of our concentration versus time. So what I'm going to do here is I'm going to go ahead and insert a row. See, I think right-clicking, yep, right-clicky. There we go. Okay, so I will type in equals natural log, and then I've got my concentration. Close that rascal off, and then populate the rest of my data. Okay, so I'm going to do a graph that's column A versus column D. So I can go insert, scatter plot, and booyah! Got to be honest, that looks a little bit more linear. Let's go ahead and look at both of them. I'll scale this one down a little bit. Okay, so when I compare those two, this natural log one looks a little bit better. And if this is linear, this is going to be an indication that we're talking about it is first order with respect to our sodium hypochlorite. So now I'm going to go ahead and close that. Look at my R squared value. I've got an R squared value of 0.9995. Okay, so it's more linear when looking at the natural log data than when looking at the concentration versus time data alone. Now, one of the important parts about this, and I'm going to go ahead and try to return my data to its kind of original state. We collected a whole bunch of data, and let's go ahead and analyze all of that data. So one thing that I'm going to go ahead and do is I'm going to go ahead and delete my zero time point, my zero data point from all of my data sets. I'm also, because what I want to do is I want to put all of my data onto one graph so then I can compare all of this data. Now, if you look at your time points, they were taken at the exact same interval. Right now, I've highlighted the third time point, 3.65744, for my 50 mil sample, or 50 microliters of bleach. Yeah, 50 microliters of bleach. No, not 50 microliters, 500 microliters of bleach, half a milliliter of bleach. I've got the exact same time point for my one mil of bleach, and then I have the exact same time point for my 1.5 mils of bleach. What I want to do is I want to generate a graph, and actually I want to generate a pair of graphs that reflect all of my data with concentration of sodium hypochlorite versus time, as well as all of my data of natural log of concentration of sodium hypochlorite versus time. Because what I want to do is, if I'm changing the concentration in each one of my trials, I should see the same linear curve reflected in my first order reaction, regardless of the concentration of, or regardless of how my concentration changes. So I should see that same trend go on. I'm going to delete this. What I'm also going to delete are, so I'm deleting my times, my absorbances for all of my trials. The reason for that is all that I care about, oopsies, I'm going to copy all this. Oh, okay. Copy. I'm going to make a new sheet. I'm going to paste just my values. And I got a little bit smaller, so I'll give the little zoomerooski in. I'm getting rid of absorbance and, sorry, absorbance and time, absorbance and time and absorbance. I'm keeping one time point or one set of time points because I want to be able to compare them. I don't need the redundant data sets. I'm getting rid of absorbance because I don't need that. I already have my concentration, so I don't need to really worry about that. One thing that I noticed about this is my numbers here, 8.37118E is now 8.4 e to the negative 6. So I think what I'm going to do is go back to my previous data set, copy it, and now I'm going to paste, where are we, formulas. Okay, I'm just going to try to copy formulas, or does that, oh, there we go. Okay, so sorry, I copied my numbers and they're all there. Values, there we go. All the numbers are there, so that was just a rounding thing based on how the cells were presented. Okay, so at any rate, my first time I'm getting rid of my first absorbance. My second time I'm getting rid of my second absorbance. I'm getting rid of my third time my third absorbance. I'm going to delete all these. My data set's going to get a little bit more compact. Okay, so I can expand all of my cells. There we go. And I'm going to say, let's see, that would be 0.5 mils bleach, CH, 1.0 milliliters of bleach, and 1.5 milliliters bleach. Okay, so I have all of those. Now what I want to do is collect or look at my entire data set, and I want to insert scatter plot. Okay, I missed one data point. That would be my 1 milliliter. Okay, I'm going to go ahead and that's another one of those very low numbers, so I'll go ahead and get rid of that. But I've got all my other data points. And what you notice is all these data kind of look the same. You got that same general trend. My blue data set is my 0.5 mil bleach. I've already looked at my R squared value, but I want to go ahead and display all of my R squared values. That was my 0.9746. My next data set, add my trend line, display R squared value. Well, that's R squared is 0.9007. Ooh. So we're moving away from it being linear. So display R squared value now is 0.8208. Oof, that's tough. That's a tough one to be happy about there. But your takeaway from this is that our first idea of, well, it's not linear is pretty darn accurate. So now what I'm going to do is I'm going to come up with the natural log graph with all of my data. So this data set that I've collected, this is pretty much I would say a compelling argument that we're not talking about our reaction being 0th order with respect to the sodium hypochlorite. What I've done is I've selected all of my data and I've copied it. I've pasted into a new data set, so I can go ahead and copy some of my other data. So I'm going to copy A into column F. Now what I want to do is I want to go ahead and say 0.5 milliliter, 1.0 milliliter, and 1.5 milliliters. The reason for this is going to show my variable concentration of sodium hypochlorite. I'm going to select equals, then select cell B2. Wait, nope, I'm not. Select equals natural log, and then B2. Enter. And I'm going to populate all of those data. Now equals natural log, and well, C actually has nothing in it, so, but the rest of them are good. And then equals natural log, copy that. Oh, what happened there? Parentheses, close parentheses, and go through. I'm going to delete this one though. Okay, so now I've got all my natural log data versus time. So what I want to do is go ahead and select all of that, insert scatter plot. Lo and behold, here's my scatter plots. I want to do the exact same thing as what I did previously. So I'm going to go ahead and this data is my 1.5 mil. So I actually haven't plotted that. I don't want to ruin the surprise. So I'm going to select the 0.5 where my R squared value was 0.999999995. It wasn't really that many nines, but I hope that you get my hilarious humor. Now my next is 1 milliliter of my sodium hypochlorite, and I've got a value of 0.9988. And then my last is my trend line for my 1.5 milliliters of sodium hypochlorite. Plug that in, R squared equals 0.9969. So I've got some data here that very much so supports what I've previously seen with it is first order with respect to sodium hypochlorite. Now, the last thing that I'm going to do is I'm going to take my data that I previously generated from my first analysis where I was looking at time versus concentration. So this is the sheet that I just completed. This sheet shows me that I've got on the left-hand side of the screen, I've got my concentration and time. I'm going to copy that and paste it into a new sheet. Again, it gets a little bit smaller, but what I want to do is I want to look at each one of these values divided by, or sorry, the reciprocal values of them. Oopsies. Click that. Okay, there we go. Oh, that's not what I wanted. B2, Dunzo. Okay, well, that's interesting. 119,457. Well, that kind of makes sense though, because what I was talking about was a very, very small number that I was taking the reciprocal of. want to do the same thing. I'm going to skip this cell G2. I'm going to say equals 1 divided by that. Close equals 1 divided by that. Okay. And I'm going to highlight this. I'm going to go all the way down. Data. Done. Populated. Populated. Last thing I'm going to do is copy my times. So now I can copy my other axes, paste. Sorry, I got to go ahead and cut all of that. And then I'm going to paste. I'm just going to plug that in. There we go. I got the same numbers. Okay, so I've moved it just to give it a little bit of space to breathe. Now I'm going to go to insert. I'm going to put together a chart. Scatter plot. Lo and behold, what on earth? We had this plot. They're going down. We had this plot. They're going down. Okay, so we've put together all of these different values, but the most important thing, and the question that we're asking, is which one of these graphs plots our data in a linear fashion? Now, simply looking at this data, you can tell that, well, linear means if it goes up in one dimension, it goes up in the same, or in the other dimension. If it goes down in one dimension, it's going to go down in the other dimension. It's going to consistently do that. You can look at this data and say, well, that's not linear, because our move from 20 seconds to 25 seconds is greater than our concentration or reciprocal concentration from 10 to 15. And from 35 to 40 is greater than our 25 to 30. So it kind of shows you that this is not linear data, in which case we can safely dismiss that our reaction is second order with respect to sodium hypochlorite, which we're already kind of going in that direction because our natural log graph looks really, really great. All right. So now that we've collected all of that data, we've plotted all of that data, we've looked at our graphs as being linear or not linear, and we've kind of made an early proposal as to what the order of our reaction is. What we need to do is we need to find out our y value. And our y value is going to be equal to the natural log of the rate 1 over rate 2 divided by the natural log of NaOCl divided by the concentration of NaOCl2. Now, what we're going to do is we're going to use the method of initial rates to find that y value. And so what we have is we have an idea that sodium hypochlorite is basically constant in early parts of the reaction. And so it's not being consumed and utilized, so we can actually see directly how it is impacting the overall reaction. Now, in order to determine an initial rate, what we have to do is look back at our graph of concentration versus time. But what we have to do is use a limited amount of that data. Now, if you look at this data set that I've got right now, up on the screen, what I'm going to do is I'm going to copy seconds 2.43829 through seconds 7.3, or yeah, 31488. I'm going to open a new window or a new sheet, copy that in there. Then I'm going to go back to where I was. I'm going to copy my time versus amount of bleach, copy that in there. And now we've got that right there. That's our time versus our concentration of bleach. Now, I'm going to highlight all of this and I'm going to plot this. And the reason that I'm going to plot this is because the method of initial rates, what I need to do is I need to plot all of my data and look at the slope of these lines. Now, what's important about this data set is that you want to plot it where you are looking at an R squared value that's very high. So you want to get basically the most linear data set and plot that. So I'm going to, and I also, sorry, I want to include my equations. So the second one that I just moved, that is my data set for that's my orange data set. I'm going to look at my blue data set here. I'm going to include my equation for my graph. So I've got I'm going to move the data right over the amount of bleach. Okay, amount of bleach. I'm going to move this up here. Oh, not that. I want to move this right here. And then gray data, add trend line in my equation. Now, what's important about this is you're not moving, or you're not using a set or a fixed range. So, you know, for you, it might be seconds 1 through 5, or seconds 1 through 9, or 2 through 8, or something like that. You want to try to avoid using a range of time in which your data is no longer linear. And, you know, this is kind of tough because, as you can see, our data gets very unlinear very quickly. But this is basically what you want to set up. And so with that, what we're going to do is we're going to calculate our y value. So we have those values, but one thing that I'd like you to do is go ahead and do what we did previously and put together this data where we're not looking at the entire graph, but instead selecting the range for the slope and having the slope be calculated independent of the graph. So here it gives you more significant figures. It's helpful to kind of visualize that a little bit more. Slope. Comma. Close. This doesn't change anything about the graph itself, but you get data that's a little bit more detailed or more precise, as it would be. I'm highlighting my known y values, which is my concentration, and then pressing comma, and then highlighting my known x values, which are my time points. So these are all the values that you're actually going to need moving forward. So now what I do, or what I have, is I have my initial rates for each of my reactions. So I'm going to go ahead and copy all of that into this table right here, the one that we've previously looked at, where we were kind of giving the lowdown for what our reaction consisted of. So initial rate, I'm going to copy all these, but then, oh, did it not? Oh, man. Copy, paste. Oh, nope, that's not what I want because it's pulled. Yeah, okay, copy. Paste. Okay. Cut. Paste. Cut. Paste. Cut. Paste. Okay, so there's all my initial rates. Now, what I want to do ultimately is I want to compare my initial rates to concentrations. And so I can take the natural log. Let me go ahead and write this out. Natural log of, what's going on? Okay. Rate 1 divided by natural log of rate 2 divided by, and this is going to be my natural log of concentration of OCl 1 divided by concentration of OCl sub 2 divided, yeah, that is equal to my y value. So since I have a total of 3 different values here, or 3 different rates, I want to go ahead and come up with all 3 of those different y values, and then come up with the average for those y values to give myself an overall y value. So to do that, I'm going to go ahead and set this up as, I'm going to try to do all this in Excel. Nope, that's wrong. I'm going to set up equals parentheses, natural log, parentheses, rate 1 divided by rate 2, close parentheses, divided by natural log, parentheses, concentration 1. So that would be in this L4 divided by L5, close, close, done. Okay. Equals. So putting that in isn't too difficult. I'm going to go with 2 to 3. So I'm comparing rate 2 and rate 3 with one another, divided by natural log of concentration of bleach. Oh, I'm missing something. Concentration of bleach divided by concentration of bleach, close, close, close. And then finally, we've got, I'm going to do 1 to 3. So parentheses, natural log, oh, rats. Natural log, parentheses, this divided by this divided by, what are we looking at there? Natural log, open parentheses, concentration 1 divided by concentration 3, close, close, done. Okay, so those are all my initial rates, and those are all of my Y values. So what I'm going to do, and I'm kind of running into a little bit of a jam because we have a negative Y value. So now I want to go back and illustrate these numbers a little bit more. I'm going to go ahead and put this as my Y value, or Y values. But I want to go ahead and explain this a little bit more, just in case that demonstration was a little bit confusing. So what we have is we're comparing different rates. So I'm going to make this column here just to show all of my information. I want to compare rates, rate versus rate. Okay. Now, one way that I can do that is by setting equals this rate number 1 divided by initial rate for trial number 2. Then what I want to do is I want to go ahead, and this is rate or trial 1 versus trial 2. You can go ahead and expand this a little bit. Trial 1 versus trial, actually I think what I did was trial 2 versus trial 3. And then trial 1 versus trial 3. Okay, so I'm going to set up 1 versus 2, 2 versus 3. So 2 versus 3 is going to be this divided by this. Okay, next up is 1 versus 3, 1 divided by 3. Okay, so there's all of my rates. The next thing that I want to do is I want to be able to look at my natural log. So I'm going to type in equals natural log, parentheses, equals natural log, parentheses, that number. Oh, rats. I need to copy that, paste that. Okay, natural. Okay, next up is ln of 2 divided by 3, close, equals natural log of 1 divided by 3. So then concentrations. I'm going to label that concentration comparisons. Okay, so close this rascal so I have a little bit more space with which to work. Concentrations for trial 1 versus trial 3. Well, this is a ratio of my final concentration at the start of that trial. Okay, so 0.5 molar, or 0.5 is my ratio. Trial 2 to 3, 2 to 3, and then 1 to 3. Okay, so then my next one is natural log of concentrations. Okay, so equals ln parentheses, nope, P9. That's the cell that I'm working with there, equals natural log of that one, equals natural log of that one, close. Okay, so once I have all of that information, now it's a little bit easier for me to work through or to display what I wanted. So my Y values, I'm going to be comparing the natural logs of my concentrations as well as my rates. So I'm going to say trial 1 versus 2, trial 2 versus 3, trial 1 versus 3. Okay, so this is equal to natural log of my rates divided by natural log of my concentrations. 1.23 or 1.299369946. That's exactly what we got up here. Okay, Next up is rates divided by concentrations. Again, oh, wait a minute. Why was that -2? What did I do? Okay, so I'm just going to try to punch this in again. Natural log of my rates divided by natural log of my concentrations. And done. -2.22. Huh, what did I do wrong? I did something different there, 5 to 6. Unless that was a comparison. 5 to 6 was 2 to 3. Natural log of N5 to N6, so those are my rates, divided by the natural log of L5 to L6. Huh. Well, suppose that it's, oh, I see what I did. Natural log of, I think I see what I did. Natural log of N10, oh, I made a mistake. Okay, sorry about that. So this is going to be natural log of my rates, and I'm going to plug that in. Okay, so there, that whenever I plug that in, that changes my Q16. Now this guy is just going to be, I think, yeah, I was typing in the wrong thing. I was adding an extra part to my formula, and I did not need to do that. So natural log of this, done. Okay, so now, finally, trial 1 versus trial 3. This is going to be equal to natural log of my rates divided by natural log of my concentrations. Done. 0.625. Okay, so all those numbers can be reconciled with one another. So that's what you need to do in order to set up all these different calculations. Now, when it comes to, you have 3 different y values, we want to go ahead and figure out the average of those y values. So I'm going to go ahead and plug that in, is equal to average, and I'm going to take those 3 numbers. Where is my typo? Yes, I typed in AVG and it tells me no, that's not right, and you need to type in average. I will accept that correction. Okay, so my y value is 0.465741,899. Now, looking at our data, one thing that stands out to me is our y value for a comparison of trials 2 and 3 is negative. I wouldn't really expect that, but I think that probably is something that you could change based on the data points that you select and how linear those 2 individual graphs are. So that's something to keep in mind whenever you're actually putting your data together. Now, one thing to keep in mind with all of this is, what is this y value? Well, our y value is effectively, when we look at our overall rate function, we're looking at, rate is equal to K times concentration of FD and C to the xth power, and then NaOCl to the yth power, okay? We were expecting y to be 1 because we were expecting this to be first order or a first order reaction. Well, our y value is 0.465. Now that is, let's say, not equal to 1. And so that's kind of an internal check of, well, this number, the data points that we selected for our initial trial maybe weren't the best data points. In part because we have that negative number, but also because our overall average for our y value is our overall average is less than 0.5. So that's one thing to kind of keep in mind and think about with the data that we've collected and analyzed. So now what we have is a number of different data points but also some numbers that we can use ultimately to fill in. So we're going to use this, not the mouse, the draw function. We're going to use this equation. It's our understanding that we have an FD and C curve that is 1, and our x value is going to be 1. This y value we figured out to be 0.467 or 4657. Now what we want to do is we want to find out our k value. So what we're going to use is a couple of different data points from all of the different trials that we've gone through. So with the data that we have all displayed here, what we're going to do is go ahead and make some calculations taking into consideration our 3 different trials. So I'm going to go ahead and say trial number 1 through 3, T1 through 3. Now, what we need to consider there is what is everything that we put into our reaction? Well, we put FD&C and NaOCl. So what we want to do is we want to look at a rate, we want to look at the concentration of FD&C, we want to look at the NaOCl, and we want to look at our X and Y values. Now, what we've got here is we have our concentration, initial FD and C concentration. So our dye concentration is going to be this 3.366 times 10 to the negative 6th. So that's the initial concentration in our reaction. Okay. Now, or sorry, that's the initial concentration at the beginning of the reaction, because that was the concentration that we used in our overall reaction. Okay, so then what we wanted to do was we wanted to look at initial NaOCl, sodium hypochlorite concentration. And that sodium hypochlorite concentration, we're going to use these, 0.1233 and so on. Okay. Next up is going to be our Y value, and that is going to be our 0.465742. Now, what we can use, so basically if you're kind of playing along at home with all the things that we've referenced from this equation down here, is we've got our FD&C concentration, we've got our NaOCl concentration, we have our X as 1, we have our Y as 0.465742, okay? Now, what we want to do is we want to do the algebra to rearrange this so that we can isolate K. And so what we'll do is FD&C to the Xth power NaOCl to the Yth power, divide by each side, and that's going to give us this equation right here. Rate divided by FD and C to the Xth power times NaOCl to the 0.4 or to the Yth power. That is equal to K. And so what I want to do is I want to go ahead and set this up. So I want to set this up, and I'm going to go ahead and try to do it using Excel. So my K values, actually I'll go ahead and copy my initial rates. My initial rates were up here. I'm going to copy those, paste. Okay, now my K values, K equals question mark. What I'm going to do is try to set all of this up as an equation in Excel. So this is equal to my rate divided by my FD&C. And so what I like to do is I'm going to go ahead and see if this works out for me. I'm going to say divided by, and then parentheses, I'm going to say my FD&C concentration, close parentheses, and I'm going to use the caret symbol, meaning to the whateverth power. So that's to the first. Then I'm going to open a new parentheses. That's going to be where I put the NaOCl concentration to the Yth power. Okay, plug that in. Oh, there's a typo in my formula. I think that it's just as simple as a, okay, close. Yeah, we're good there. Okay, so it told me that I didn't have enough parentheses, or I had too many parentheses. Yes. No, I didn't have a multiply sign. Okay, so I'm going to click yes. Okay. Now, so what I've got now is a K value that is negative 0.1606 96959. What I'm going to do is go ahead and use that exact same equation to solve for my other functions. And what I did was I just sort of set it all up in one specific, or in one cell. So I think that I can expand some of these cells and give you a little bit more space to see it. It's equals G23, which is my rate, divided by D23, which is my FD&C concentration, raised to the first power, multiplied by E23, which is my my NaOCl concentration raised to the yth power. Plug all that in, do that for all of the rest, and there's your value. Now, to write the entire rate law, it's going to look a little bit like this, and I'm going to do it in red. And so this is rate is equal to, now, one thing to keep in mind before I continue is that our K value is going to be positive. The reason that it displays as negative is because of the fact that we were looking at we had our initial rates as negative values. Now, what I'm going to do is I'm going to go ahead, since we have 3 of them, I'm going to come up with the average for those 3. So I'll plug all those in equally, divide by 3, plug it in. Okay, so I'm just going to, on the fly, convert this to a 0.212 times my FD&C concentration to the first times our NaOCl to the 0.466 power. There's my rate law. Now, keep in mind, our numbers probably aren't the best. And so if you were doing this, so if you were, I don't know, you were genuinely trying to figure out this reaction for, for another purpose, and you have kind of unlimited resources, I would do it again. I would do more trials, and you can probably fine tune those numbers. So that's basically it for all these sorts of calculations. It's probably not going to take you as long to come up with these calculations and put all these graphs together. You do 1 or 2, and then it gets a little bit easier to plug those in. I would strongly recommend using all those little functions that you have in Microsoft Excel so that you can save yourself a little bit of time. And just go back and double check. And generally, when you double check, you're going to find probably where you went awry, which is what I did earlier.